Welcome to The Explainer. Today, we're going to fundamentally reshape how you think about gravity. We usually just think of it as that invisible force keeping our feet firmly planted on the floor. But we're going to start really big, zooming way out to the entire solar system, and then we'll dive all the way down into the crust beneath your feet to reveal gravity for what it truly is, a dynamic, ever-changing sculptor of our reality. So let's kick things off with a couple of questions that might actually challenge what you were taught in grade school. First, is a day exactly 24 hours? And second, is the Earth actually a perfect sphere? Well, as we dig into the real physics of gravity, we're gonna uncover a story that's way stranger and honestly way cooler than those simple models we're all used to.
Which brings us to part one, the cosmic dance.
Okay, picture this. Back in 1687, Sir Isaac Newton had this massive, light bulb moment that literally changed physics forever. He realized that planets, well, they naturally just want to fly off in a straight line into deep space. But the sun's gravity provides the exact centripetal force needed to constantly reel the planet back in, bending its path into a circle. So an orbit isn't some magical track in space. It's basically just a continuous, perfectly balanced freefall. Moving on to part two, the moon's tugging act. Let's bring things a bit closer to home. The moon's gravity pulls harder on the side of Earth facing it, right? And that creates a tidal bulge. But because the Earth's crust is actually a bit pliable, kind of squishy on a planetary scale, and we're rotating way faster than the moon orbits, that bulge doesn't point directly at the moon. It actually lags behind, spinning forward by about 12 minutes. It creates this absolutely incredible gravitational offset. And because of that 12-minute offset, something totally wild happens. That tidal bulge, which has spun slightly ahead, uses its own gravitational mass to physically pull the moon forward in its orbit. It's literally transferring angular momentum from the Earth directly to the moon. The crazy results? The moon is stealing our momentum and retreating away from us by 3.85 centimeters every single year. Now, the total momentum of the Earth-Moon system is a closed loop, meaning it absolutely has to be conserved. So there's a fascinating trade-off happening right under our feet. As the moon speeds up and moves further away, the Earth's rotation has to slow down to compensate. It's a tiny fraction, sure, but our days are literally getting longer by about 0.00013 seconds every year. You're definitely not going to feel it when your alarm goes off tomorrow, but over millions of years, this dramatically changes the fundamental length of a day on Earth. All that changing rotation leads us perfectly into section 3, the wobbling spinning top. Think of the Earth like a giant spinning top that's constantly being gently tapped. As seasonal weather shifts massive amounts of water, snow, and ice around the globe, or, when major earthquakes move tectonic plates, the Earth's internal mass distribution changes. All these forces beat against a natural 438-day cycle called the Chandler wobble. And on a much more massive scale, the moon's gravitational pull on our equator causes our entire axis to slowly rotate or precess over a mind-boggling 25,772-year cycle. Because of all this continuous wobbling, true north isn't actually a fixed point at all. It wanders. If you track the data precisely, our geographic North Pole has traveled in this weird, spiraling path, moving almost 12 meters away from where it was back in 1900. Literally, the ground you're standing on is constantly shifting its orientation in space. Which brings us to section 4, Earth's lumpy shape. So, because the Earth is spinning at over 1,000 miles an hour, there's a powerful centripetal acceleration acting right at the equator, essentially flinging material outward. This outward force literally counteracts a tiny fraction of gravity, and because that inward pull of gravity is effectively lower at the equator than it is at the poles, the Earth bulges outward in the middle. Its equatorial radius is noticeably larger than its polar radius, by about 1 part in 298. Our spin is fundamentally warping the shape of our world. To truly map this out and wrap our heads around Earth's uneven gravity, geophysicists use a brilliant conceptual model called the geoid. The geoid maps the true gravity-defined shape of the Earth based entirely on its internal mass. Imagine if the oceans were perfectly still, covering the whole planet, influenced only by gravity and rotation. That undulating surface? That's the geoid. It shows us exactly where mass is super dense inside the Earth and where it's a lot lighter. And when you look at it through the lens of gravity, our planet doesn't look like a perfect sphere at all. It's essentially a giant, lumpy potato. For example, there's a massive mass deficiency south of India that creates a literal 107-meter depression in the gravitational surface. Meanwhile, over near New Guinea, extra dense mass creates an 85-meter gravitational high. Finally, let's zoom all the way down to the crust for Section 5, the gravity of mountains. Okay, picture this. It's the 1830s and a surveyor named George Everest is mapping India. To find true vertical down to the Earth's center, surveyors use a weighted string called a plumb bob. But near the Himalayas, Everest stumbled upon a huge mystery. The colossal mass of the mountain range was actually exerting its own gravity, pulling his plumb bob sideways. But here's the catch. It wasn't pulling it nearly as much as the math dictated it should. Calculations based purely on the visible mountain predicted a deflection of nearly 16 seconds of arc, which is a tiny but highly measurable fraction of a degree. But Everest only measured a 5.24-second deflection. A huge chunk of the expected gravitational pull was simply missing. The Royal Society of London was totally baffled. I mean, where did the missing mass go? This actually sparked a fierce debate about isosity, which is basically how the crust floats on the fluid mantle below. A scientist named Pratt thought maybe tall mountains just had a uniformly lower density, but George Airy hit the nail on the head. He realized mountains don't just sit right on the surface, they have massive deep roots hidden deep in the crust, floating in the heavier mantle exactly like icebergs floating in the ocean. And here is the absolute genius of it. Because these deep mountain roots are made of crust, which is less dense than the heavy mantle rock they're pushing out of the way below, they represent a relative mass deficiency. This missing mass, deep underground, perfectly subtracts from the gravitational pull of the towering mountain above ground. And that explains exactly why Everest plumb bob wasn't deflected nearly as much as he expected. As we wrap up this explainer, I just really want you to think about how incredibly dynamic our physical world actually is. Every single second of your life is subject to this delicate cosmic balancing act. The moon stealing our spin, the poles wandering under our feet, a lumpy gravitational field mapping hidden densities, and giant icebergs of solid rock floating beneath the mountains. Knowing all of this, does it change how you feel about the solid ground you walk on? What are you going to look up and question next? Thanks for joining me on this deep dive, and keep questioning.